All right, so I'm Alex Mussell. I'm a machine learning engineer at Bastian Solutions, a company in Boise. We do R&D for robotics. I was hoping to give a talk today about a lot of the things I've learned about computer vision over the past 6 months of working in the field. I remember when I first started learning how to program, you have to learn how to think like a programmer, right? Somebody comes to you with some kind of business problem or something like that. You have to figure out how to frame that problem as, in terms of functions and classes. And machine learning is very much the same way. If somebody comes to you with a problem, you have to figure out how to frame that problem in terms of the tool you have available to you in machine learning. I also want to make this talk accessible to anybody who has a this clicker doesn't work. To anybody who has a computer science degree, so you don't have to have too much experience in machine learning and like supervised learning, that sort of thing. So I'm going to do hopefully what will be a brief introduction into supervised learning and neural networks. Let's take that out. So within supervised learning, it's a subfield of machine learning. It's all about trying to learn functions. So let's say you want to make a function that does Face ID, like you guys might be familiar with iPhones. You can look at them now and it takes a picture of your face and determines if that's an image of your face or not. Right? Writing that function with for loops and if statements, that sort of thing, really, really hard to do. People try to do it for a long time. It turns out it's a lot easier to take a lot of data and learn the function from the data using supervised learning. Another example of a function that would be really hard to learn would be object detection. If you take an image and you want to detect where objects are within that image, you want to know where all the people are and the bounding boxes for those people, maybe guitars and harmonicas and other types of things. Really hard to write, but much easier to learn if you have a lot of data. So if you want to frame a problem as a supervised learning problem, there's three things that you want to do. The first thing is you have to express it in terms of a function, and you need to map all your concepts into numbers. So for face detection, you have an image that's coming in, and luckily an image is already a sequence of numbers. If you're not familiar with how images are represented in computers, it's a sequence of pixels. It's like a 2D or three-dimensional array of a bunch of numbers. So that's too hard, but if you're doing like NLP, like word processing, something like that, maybe you want to make a chatbot that answers questions for people, then it becomes much more difficult, right? You have to take maybe a sequence of words, which is a question, and return a sequence of words, which is an answer, and mapping words into numbers. Depending on how you do that can have a significant effect on how well your algorithm is going to work. And you kind of have this problem on the tail end of computer vision. So like detecting bounding boxes, a bounding box isn't necessarily a sequence of numbers, but there's ways you can represent it as a sequence of numbers. And depending on how you do that, it can have significant effects on the problem. The other thing you're going to need is data. So you're going to need a lot of data, especially if you're using neural networks. So if you're doing face detection again, you're going to need tens of thousands, maybe millions, if you want a really good face detector of images, of faces, and who those faces are. If you're doing object detection, again, you need maybe millions of images. There are millions of things and where they are within images. And the last thing you're going to need is what's called a loss function. The basic idea here is you need a way of determining how close a guess of an answer is to the actual answer. Right, so if you have a dog detector function, it's supposed to take an image of a dog, and maybe you're supposed to output 1 if it's a dog, and 0 if it's not a dog, and then outputs 0.97. In this case, it's pretty easy, right? You can use something like mean absolute error. You take the difference between the two answers, and then you take the absolute value, and that's kind of how far you were away. But if it's a bounding box, how close is the guess bounding box to the other bounding box, or how close is a sequence of words close, or one answer that's maybe not the exact sequence of words you were looking for, close to the actual answer. These kind of questions can become a bit more complex. So telling you that neural networks are function approximators, it's pretty abstract, pretty high level, and I'm not sure it gives you enough of an intuition that it wouldn't satisfy me, at least. So TensorFlow has a really cool website that they've developed for kind of giving people an intuitive understanding of what's going on inside of a neural network. So what they have here is they have a few different data sets you can use. Over on the right, you can see. We'll just start with this one. And so the basic idea here is this data set has two classes of points. You have blue points and orange points, and each point has two features associated with it. Right? It has pretty much just the location of the point. You've got the point's location. Point's location on the horizontal axis and the point's location on the vertical axis. And if I ask you guys, if I have this point right somewhere around there, what class is that going to be a part of? You can tell me. It's in the middle of the image. That's a blue point, right? If I give you another point on the outer ring, we can easily see that that's an orange point. Writing a function to do the same thing can be more difficult. It's a great learning tool to show how a neural network can learn that function. So I'll just start by clicking train here to begin with, to kind of show you. The neural network has parameters that are called weights that can be trained. You can set them to learn different functions. So depending on what weights you set for the neural network, it will output different values. And training it is the process of trying to find the optimal weights that fit the data the best. Neural networks are made up of smaller components called neurons, and I'm going to dive a tiny bit into what those look like, to kind of give you an understanding of what's going on under the hood. So before, in our first layer, we have these neurons that are taking in two features, which is the location of the point. And this is kind of what the internal part of that neuron looks like. So for each feature, this one has 4 features. Ours would only have two, the ones I just showed you. But for each feature, there is a weight associated with it. And it takes the value of the feature. So if it were a point that's maybe it has the coordinate 2, 2, it has a location of 2 on one axis, you would take the weight, multiply it by that. And you do that for each feature, and then you sum all those together, pass those through an activation function. And the activation function could be like a sigmoid function or a ReLU function. There's a lot of different activation functions you can use that will give you different properties. That's a topic that might probably be on the scope of this talk. And so, let me get some water. So, you can see in the first features that are given to us, they only tell us really simple information. Like with this x1 axis, we can tell if the point's in the left half or the right half of the image. We don't know where it is in terms of like the top or the bottom, right? So the other feature can tell us where it is with the top or the bottom. And what's kind of cool about this tool is it shows you for each neuron what it's outputting for every data point. So if you hover over one of the neurons, if we pass through the point up in the top, which is -6, 6, this neuron is going to output a blue value. They have a scale to the bottom here, which is 1. If that makes sense. So, and they do that for every single pixel across. So you can see how the neural network would classify, or how this neuron would classify a point that's at that pixel point. So if we were to pass that point in. And so the features that are learned in the first layer are really simple, right? So if you look at this one, it's learning points that are in the bottom right corner and the upper left corner, right? It's learning to distinguish between those two things using just the features from this, using just these two features. You get some kind of similar sorts of behavior. What's kind of cool is if you add in a few extra layers and train this a little bit. Let's do a little bit further. You can see some more complex features. So this node here specifically is learning points that are in the center of the image, and this one is learning things that are not in the little wedge on the left there. And so these are all just kind of combinations of the features before it, right? So if you know something's in the left, you know something's in the bottom, you know things that are in the bottom left, right? If you know things that are in this section and that section, you can get an intersection and learn a more complex feature in feature layers. And just for fun, we can kind of see how this can kind of generalize to more complex. Like, I don't know how you'd write a function to detect, to classify these points, but given enough training, I think maybe around 500 iterations or so, we do a little bit of feature engineering, it'll converge a lot faster.
What about overfitting?
What?
What about overfitting?
Yeah, this would be probably a case where it's definitely overfitting. That we could probably give a whole talk about neural networks and overfitting. So you can see it starts to learn something about the data distribution. It definitely looks like it's being overfit, I would say, from this here. So what I just showed you is called a densely connected neural network. And unfortunately, the network I just showed you only took in 2 features. Right? With an image, with even a simple black and white image, it's maybe 200 pixels by 200 pixels. You have 40,000 pixels, 40,000 features that have to be fed into the network. And the more weights you have to kind of look for, every feature that gets passed in has weights that are associated with it, and you have to learn those weights, as you saw when we were training the network. And it takes a lot longer to fit a lot more weights, and you have problems with overfitting, like you were talking before. And so convolutional neural networks are kind of the way that we handle images, because there's so many features that we have to learn. With convolutional neural networks, you have to learn a lot less features. And they're built on top of like densely connected neural networks are built on neurons, convolutional neural networks are built on top of kernels. So the kernel is a pretty simple function. Here we have a 3x3 kernel that's being that's processing an image. And the way you apply a kernel to an image is you take the kernel and you apply it to every single sub-window of the image. There's actually, I have a pretty good GIF that shows what that looks like. So here you have a 3x3 kernel that's sliding over the image and it's producing an output image as it does that. So for each sub-window, it computes a new pixel in the output image, if that makes sense. And so what it's doing to compute each pixel in the output image is not a super complex function. It just takes the element-wise product between the sub-window and the kernel itself and then sums them together. So in this case, it's like 0 times -1 plus, I can't keep my hands still enough to get there, but 0 times -1 plus 0 times -2 plus 75 times -1 plus 0 times 0. And all the way through, if we did the math, you can see that you get 155 for that specific pixel. And you just slide it across to keep doing that operation. What's pretty cool about this is depending on the values that you put within this kernel, you can produce different kinds of images. So in this GIF, they've constructed a kernel that is doing vertical edge detection. It's got like negative values on the left half and right, and positive values on the right half. And as it slides over, you can see when it gets applied to like an edge within the A, it produces a rising edge, or green values in the output image. Then when it goes to a falling edge, you can see the red values in the output image, and you can kind of see how it's doing this, this vertical edge detection. So somebody ran an edge detection kernel over this person's face, and you can see how they can produce a way simpler representation of the image. So just like how in the neurons we had the weights, which were you could change the parameters, right? You can change the weights to learn more complex functions. You can change the values in your kernel to learn different types of feature detectors, right? You can learn vertical edge detectors, horizontal edge detectors, you can learn diagonal edge detectors, and quite a bit more. Typically, you wouldn't deal with black and white images. You're dealing with color images. And so a color image is actually made up of 3 channels of information. You have your red channel, your green channel, and your blue channel. And so just like with mixing paint, you can make different colors with combinations of red, green, and blue. You can make different colors of an image by mixing different channels of red, green, and blue. And so I showed you guys how you can apply a two-dimensional kernel to a two-dimensional black and white image. You can apply 3-dimensional kernels to 3-dimensional images in a very similar fashion. And so in the first layer of your convolutional neural network, we could by hand construct features that did, maybe we could create a vertical edge detector and create a single one-channel image that has vertical edges, like I showed before. And then you could take another kernel that does horizontal edge detection or diagonal edge detection and create another image. And you can stack these on top of each other and have, instead of an RGB image where you have 3 channels of red, green, and blue, you could have a multi-dimensional image that has a channel for the vertical edges, a channel for the diagonal edges, a channel for all these different types of information or these features that you're looking at. Kernels can also do more complex operations like detecting textures. So you can design a kernel that does like detect smooth surfaces within an image, or you can design a kernel that does detects rough textures, that sort of thing, or even detects certain colors or color ranges and that sort of thing. And so you could take a set of kernels that do, like I said before, vertical edge detection, diagonal edge detection, maybe some different colors that you want to detect, maybe some different smoothness or textures that you want to detect. You can get a really complex set of images. So instead of being a 3-dimensional or 3-channel image, you have maybe a 10-channel image with all this feature information. And then you can design kernels that process that kind of information, and maybe you can take the horizontal edge channel and the vertical edge channel and the diagonal edge channel to get maybe like a circle detector or something like that, right? You're putting together all this edge information to get more complex features. And so as you have another stage of your convolutional neural network, you can have shape channels, and you can have maybe multiple shape channels. So you have circle channels, rectangle channels, triangle channels, or it could be complex polygon shapes like maybe faces and things like that as well. And you can take those even a step further, and maybe you want smooth faces versus rough faces, or maybe faces that have textures of fur, something like that, if you're detecting animals versus humans. Eventually you get an image that is no longer, I think I may have forgot to mention, when you pass a kernel over an image, you get a smaller image as an output. And so as you continue to do this, your image is getting smaller and smaller, but it's getting more and more feature rich. So you know things about whether or not it's, you know if you've detected faces with eyes that have smooth skin, or faces with eyes that have rough skin. You have channels for all those kinds of information, and you can pass that through a densely connected neural network and start to predict maybe simpler things like whether or not there is a person in the image. So why are CNNs such a big deal? Back in maybe the early 2010s, there was a data set called imagenet, and it was developed at Stanford. It's about, at the time I think it was about 3 million images of different things. Like they have like maybe a few thousand images of huskies, and they're all labeled that they're of huskies. And they have thousands of images of different kinds of boats, and they're labeled with those tags. And they came out with a challenge called the imagenet challenge, which the goal was to create some sort of models. It could be an AI model or just a function, I suppose, that would take an image and predict which one of 1,000 different classes that image was of. And prior to 2012, nobody had used a CNN in this challenge, and the error rate was 26%. So 26% of the images that were passed in were classified wrong. AlexNet was the first CNN that was used in this competition, and it's kind of considered a landmark event within computer vision. People had kind of heard about convolutional, or CNNs, convolutional neural networks, before this, but the usage of them just kind of exploded after people saw how well AlexNet did in the imagenet challenge. And every year after that, every single one of these entries is a CNN. And so, I guess semi-recently, we actually surpassed human performance in image classification, which is kind of a hack. But you ask a human to determine which one of 1,000 classes an image is. It's hard to remember all 1,000 classes, and I'm sure that has something to do with it. If we were only 3 classes, the results might be different. But AlexNet was using, just a very similar architecture, like I was telling you about before, a few convolutional layers that are doing this kind of feature detection I told you about, and then a densely connected network. And the last thing they add to it is a softmax layer. And what a softmax layer does is it takes in a sequence of numbers and outputs a sequence of numbers, but it makes 2 guarantees about the output. Every number within the output will be a value between 0 and 1, and the sum of all the values that it outputs will be 1. So if you're familiar with statistics, this is a probability distribution, right? And so once you pass your image through your CNN or through AlexNet, you get a distribution where it's like, okay, I think there's an 80% chance it's a car, maybe a 10% chance it's a truck, and it would distribute the rest of the probability amongst all the other classes. Image classification isn't always the only thing we want to do. If I can detect a person within an image, or if I can detect that there is a person in an image, I might want to know more information, like where is that person within the image. And to do that, you want to use what are called two-stage object detectors. Our CNN was kind of the first model to introduce this approach. And what they did, which was really interesting, is they figured out how to take an image classifier, like AlexNet, or there's a lot of others now, like BGG or InceptionNet. But take an image classifier that just takes a whole image and tells you what's in it, and turn that into an object detector where it actually localizes the image and gets a bounding box within the image. So it happens in 2 stages. The first stage is you've got to come up with a bunch of guesses of where the object might be. So they use an algorithm called selective search to get 2,000 guesses. I think today people actually use neural networks to generate these guesses, but you're generating hundreds or thousands of guesses, and you take each one of those guesses. So you might guess you think somebody is about there, and you squash it so you can run it through your image classifier, and your image classifier will tell you how confident is there is a person within that image. And when you do this on all 2,000 images, the ones with the highest probabilities are the ones that are the actual true bounding boxes. So if you were to pass a bounding box that was maybe just half of the person, the classifier is not going to be as confident that it's a person because it doesn't have as much information. But when you get a tighter bounding box that's around the person and has all of them in it, you're going to get the highest score. Unfortunately, running 2,000 passes of images through a CNN takes a really long time. Like when they released this paper, it took about 40 seconds to process an image and get all the bounding boxes out. And they've done a lot of optimizations to to this architecture sense, and I think some of the newer Twostage detection networks can do like 5 frames a second, so about 0.2 seconds per image. But that's still not real time. You can imagine if you're operating a driverless car, you're going down the road, you need to detect somebody and swerve out of the way really fast. 5 frames a second may not be as fast as you need. You might want to be able to process video at 20 frames per second or 30 frames per second. And if that's what you want, then you'll need to use what's called a one-stage object detector. And so the key here is before you were looking 2,000 times, right? You're passing 2,000 different crops into your image classifier. Here you take the image and you only look once. You just pass it through one CNN and it outputs the bounding box for you. And people had tried to do this before, and there were some problems with it. YOLO introduced originally just one idea that made this work, and what that was actually segmenting the image into regions. And so you can imagine with a neural network, you have a fixed size output, right? So you can't, you're matching the image, which the image is always the same size, perhaps, but the output has to be, you can train it to 10 values or 20 values, but it's always the same. And so sometimes you're detecting 1 bounding box, sometimes you're detecting 30 bounding boxes, and how do you represent that within a fixed size output? So what they did is they came up with a description for a bounding box, pretty simple initially. You have the probability that the bounding box this region of the neural network is detecting is actually of something. And then you have the description of the bounding box, which is the x, y coordinate at the center of it, and the height and the width in pixel space of that bounding box. And then you also have the distribution of the probability distribution for what class it is. So if you have maybe 3 labels like dog, bicycle, and human, the chance that it is each, or the probability for each class that it actually is that class. And then you have one of those for every single region. So you can have multiple if you want to be able to detect 2 bounding boxes within the same region. But this was kind of the basic idea they introduced originally. And they showed that you could get, with an optimized version of the network, 155 frames a second, with obviously some performance penalty in terms of accuracy. And then in YOLO version 2, they came out with another optimization on this process, which is rather than actually outputting the description of the bounding box in terms of where the exact center is and the actual height and width, they had this idea of default bounding boxes. So within a space, if you're trying to detect cars are often the same aspect ratio. They're within a certain range, right? People too, I think it's roughly 2 to 3 for a person or something like that is a typical aspect ratio for a person. And so you have this kind of default bounding box. And what the neural network outputs now is instead of the actual height and width, it outputs corrections to the default. So it says, take that bounding box, shift it so much this way, and so much up, so much to the right, and then scale it down in these directions. And that enabled a lot of performance gains, closer to 2-stage object detectors, but still, if you want the accuracy, you gotta go to 2-stage object detection. But even knowing where the person was within the image might not be enough. If I'm driving down the road and I detect a person, now I have the bounding box from within the image of where they are, but I need to swerve out of the way of them. I need to know where they are in 3D space, not just within an image, right? So you can use depth cameras and instance segmentation to get even more fine-grained information. So what instance segmentation does, mask RCNN is a model that'll do that for you, built on top of RCNN. You don't only get a bounding box. Within that bounding box, you know which pixels are part of that object and which pixels are not. So in this case, the green pixels are part of the person, and the ones that are not colored are just the background pixels. If you captured this image with a depth camera, rather than just getting your 3 color channels of information, red, green, and blue, you get an additional channel of information, which is the depth to that point. And so now you know, from that depth, you can get a 3-dimensional point, or a 3-dimensional coordinate for that point on the person, relative to your car or whatever you're driving. So then you can actually build you can go for each pixel, you can segment all the points and build a 3-dimensional contour of that person. So you can see this is a depth image that somebody's captured here, maybe a building. But you can kind of see the 3-dimensional information. If you open this up in a point cloud view, you can drag around the image and see it from different angles. But if you capture a person, you know from the instance segmentation exactly which points are part of a person. Now you can figure out where that person is in 3D space. Maybe you have a 3-dimensional bounding box at that point. From that information, you can navigate around them or do what you want. That's all I got.